Okay, so yesterday we were reviewing our exponent laws, and today we're actually going to get into the exponential relations. So if you remember, a relation is a relationship between two variables. So there's linear relations. I guess we can do a little sketch. Linear relations make like a straight line, and that shows the way they react, the way they relate to each other is a straight line. We had quadratics, which made kind of a that shape or a that shape. And that was another way variables could react. And then this third one is going to be exponential. And we're going to explore it today. It looks a little different because it behaves a little different. Like a linear relationship, it does change sort of at a constant rate depending on how you think about it. Except instead of adding or subtracting the same amount each time, we're going to multiply or divide by that same factor every time. So that's why it's exponential, because we're just multiplying and dividing by the same amount. So let's look at a couple examples first. So bacterial growth, population growth of any kind, is something that's modeled very well by exponential equations, including human population growth. So for this one, we're going to have a type of bacteria, and it starts with a population of 100. So on day one, we have 100 bacteria. And then we know that it triples every day. So its growth factor is going to be times 3 every day. So after one day, we're going to have the 100 we started with times 3, giving us 300 after one day. After 2 days, well, we have the 300 we started with the last day times 3 again to give us 900. And we follow this pattern, and we have 2,700 after 3 days and 8,100 after 4 days. So what are some traits to help us determine if this is exponential growth? Well, number one, the fact that it's tripling. So right up here gives us a clue this is exponential growth. Well, what's another one? Let's look at our differences like we've done all year. So we'll look at our first differences. Because like always, this is our X column. I don't know why it's shifting down when I draw today. Let's try that again. There's our X column, our Y column. And then our first differences are differences in the Y values. So 300 minus 100 is 200. 900 minus 300 is 600. 2700 minus 900 is 1800. And 8100 minus 2700 is 5,400. Well, it's definitely not linear because they're very different. So we could do second differences, which is just the change of our first differences, right? 600 minus 200 is 400. 1800 minus 600 is 1200. 5400 minus 1800 is 3600. Well, it's definitely not quadratic either then. So what does that tell us? Well, you'll notice that each of these goes up by times 3, times 3, times 3. But so do the differences. From there to there is times 3. From 600 to 1800 is times 3. From 1800 to 5400 is times 3. And these ones, the second differences as well, are all times 3. So you notice that this pattern, this common ratio for the population increase is the same through the first differences, the second differences everywhere. So that's the second way we can tell that this is an exponential growth problem. So if we have an exponential relation, we use this equation right here. Y is equal to a b to the x. So a is our initial value or our starting condition. Either one works. So that is our B value for a linear relationship. That is our C value for a quadratic relationship. It's our starting value. It's our y-intercept. It's where it all gets started. And then B is what we call the growth or decay factor. And basically, it's what we multiply A by every single time x increases by 1. So we start at a value of A, and then we multiply by B every time x increases by 1, we multiply by B again. So when x is 0, y is just A. When x is 1, it's A times B. When x is 2, it's AB squared, and so on. And in this case, we actually have that in our table. If we think about it, this is 100 times 3, so we already covered that one. And this is also 100 times 3, so this is really 100 times 3 squared, times 3 twice. This one is going to be 100 times 3 3 times, and 100 times 3 4 times to get that 8,100. So that's how an exponential relationship works. It multiplies by the same factor every single time. So let's write this as an equation then. So we have y is equal to our starting value, 100, so that's our A, times our growth or decay factor. And every single time it goes up by a factor of 3. It multiplies by 3. So B will be 3, and it's to the exponent x. That's all it takes. Y is equal to the starting value times the growth factor to the power of x. Easy peasy. So let's graph this. So we're going to graph from the table of values. So our x-axis, we have to get to 4. So if I count 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, I can count to it 5 times. So 1, 2, 3, 4, there's 1, 1, 2, 3, 4, there's 2, 1, 2, 3, 4, there's 3, and 1, 2, 3, 4, there's 4. And this will be the number of days. And then my y-axis, we have to get all the way to 8,100. So let's see how many times, let's try and get to, we'll count by thousands, see how many we can get to for 9,000. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It just fits twice. So every 2 lines will be 1,000. That's 1,000, 2,000, and so on. Almost there. And this axis is the number of bacteria. And for full marks, if this was a question, we would have to write a title as well. So bacteria growth. Seems reasonable. And then we just graph our points like normal. So at 0, it's 100. So 100 is just 1/10 of the way up. So around there. After day 1, we're at 300. So that line above it is 500. So somewhere in there. 2 days, we're at 900, almost to the 1,000. Day 3, 2,700. So way up here. And day 4, 8,100. Which is way up there. So definitely not a line. And we'll do our best to do like a curve of best fit here. And it looks a little bit like half of a parabola, I'm not going to lie. It's not quite the same, but it is a similar idea in that it accelerates faster and faster and faster and faster as it goes. So this is exponential growth. So if we assume this trend continues, let's use some of our graph knowledge from way back in Spiral 1. What would the population look like after a week? Well, time is being measured by x in this case, right? Our x variable is the number of days. So after 1 week, that just means x is equal to 7. So we plug that into our formula. Y is equal to 100 times 3 to the power of 7. And you can run that through your calculator. Just a reminder, for most calculators, you've got 3 options for exponents. Your calculator will have one or the other, but not all of them. So it's either x to the y, or y to the x, or this kind of upward arrow thing. Those are what the exponential buttons will look like. That's really messy. Clean that one up a bit. Something like that. So you run that through your calculator, and you will get 218,700 bacteria after a week. Yuck. And of course, in terms of reality, we should, be a little sensible. If this was, in a lab, in a petri dish, something like that, then it's only going to be able to grow like this so long as it has enough food. But mathematically, this is what it would do if it had enough food and space and everything else. And then for 2 weeks, x is going to be equal to 14. And then it's always good to make a little sort of guess, right? If this was linear, if I double the time, I'm going to double the population. So it would go up to about 536,000, 537,000. But we can see as this graph goes, it goes up faster and faster and faster. So we expect it's going to go bigger than that. So let's see how big it actually does get. Y is equal to 100 times 3 to the power of 14. And you run that through your calculator and you will get 478,297,900. And that's a lot of bacteria. But that's everything there is about growth. We've got our nice simple formula, y equals ab to the x, which is going to be the root of everything we do with exponentials. We have our patterns to recognize how the common factor of going up times 3 every time. A is our starting value, B is our growth factor, and that's about it. But sometimes things don't work quite as nicely. So we're going to look at one that's a little bit more complicated when we look at exponential decay. So if exponential growth means that it increases by a certain multiple every single time, decay means that it's going to decrease by a certain factor every time. It's going to be cut in half or a third or a quarter every so often. And in fact, one that we see the most often is something called half-life. And half-life, in chemistry terms, is how long it takes for a radioactive element, so this is unstable, what it means is radioactive, to decay to be half as radioactive as it was. And that's what we do to measure like plutonium and uranium and all these radioactive things. So in this example, we're studying something called uranium-239. It's a radioactive material. It has a half-life of about 2 years. So every 2 years, half of it will decay into a more stable form. So we'll start with 1,000 milligrams sample. So in 0 years, right? Oops. Scrolling the wrong thing here. In 0 years, that's been 1 half-life. Or sorry, it's been 0 half-lives. 0 years, 0 half-lives, that's just our starting condition, which is 1,000. And as our starting condition, we should be realizing right away that's our A value, right? And now, it's going to take, we're going to do this one in terms of half-lives, because that's how often it halves. So our half-lives, we're going to go 1, 2, 3, 4, right? After one half-life, it's cut in half. So we only have 500 milligrams left. 2 half-lives, it's cut in half again. 250 milligrams. 3 half-lives, it's cut in half again. And then 4 half-lives, it's cut in half one last time, 62.5 milligrams. So this is our X, and this is our Y, sort of, when we're working with a weird situation like here. Because this one's a little strange because we need to work with half-lives because that's when it actually happens. This column over here of the years is just to kind of tie it into reality. That was odd. Don't know why it's being weird about moving today. So 1 half-life was 2 years, 2 half-lives is 4 years, 3 is 6, and 4 is 8 because they're 2 years each. And if you were asked to prove that this is a half-life or an exponential problem, we could check our first difference and see if that is also the same pattern. And we'll see, to go from 1,000 to 500, we went down 500, and then down 250, and then down 125, and then down 62.5. And this is the exact same pattern as we saw before, right? It's divided by 2, and so on. And these are also divided by 2, divided by 2. So as we noticed, our starting amount is our A, and this what's happening every time, is our B. So for this one, we have Y is equal to 1,000 milligrams times 1/2, because divided by 2 is times 1/2, and it's always by multiplying, so you just switch it into its fraction form, to the power of X. And we just need to keep track that X is the number of half-lives. So if an answer asks about years, we'll have to switch between years and half-lives, but that's okay. All right, so let's solve these practice problems. So how long will it take to decay to be about 10 milligrams? Well, essentially, to solve this, we just have to keep following this pattern here. And we can just do it on our calculator. So after 4 half-lives, it's 62.5. And then I'll just keep dividing by 2. So divided by 2. So after 5 half-lives, it'll be 31. It'll be 31.25. After 6 half-lives, so divided by 2 again, it'll be about 15.625 milligrams. Divided by 2 again. And after 7 half-lives, it'll be 7.8125. So when will it be 10 milligrams? Well, it'll be somewhere between here and here. And I can hear the groans right now, but this is not on purpose. It will be between 6 or 7 half-lives. And if each half-life is 2 years, that means it'll be around 13 years or so. And then you can continue on the same way for 1 milligram. And you don't have to write them down all the time, but you can. So we'll divide by 2 again. So after 8 half-lives, it's 3.9 roughly. I'll divide by 2 again, and after 9 half-lives, we're about 1.95. We'll divide by 2 again. And after 10 half-lives, it's about 0.98. So the final case will be really close to that. So it'll take almost 10 half-lives. And if each half-life is 2 years, that means it'll be about 20 years, a little under 20 years. Okay? So that's all that takes. And then we have like a conceptual question here. will the mass ever reach 0? Will it ever be not radioactive at all? So I'll give you a minute to think on that, pause the video, and then unpause it when you're ready for the answer. And how it works is, if it keeps being cut in half and in half and in half and in half, then technically it will never get all the way to 0. It can get closer and closer and closer, like infinitely close, but it will never get all the way there. It can be functionally 0, but not literally 0. So let's take a quick look at it on Desmos and look at how to do a line of best fit in Desmos, and then you're free for your practice problems. So here we are in Desmos. I've put the table in, so if you need a minute to do that yourself, feel free to pause the video. For some reminders about Desmos, when you put in a table of values, you can click this nice little zoom fit, the magnifying glass, and it'll zoom right to your points. And if you remember, in our previous examples, we basically put in an equation that looked just like what we were doing to do a line of best fit. Oh, this is a little low here. 1 second. It's not wanting to behave for me. There we go. That'll work. So if this were just doing an exponential function, we would do y is equal to b to the power of x, right? But you see nothing happened because we have to do this the way that we always ask it to give us the formula, right? So we need to reference y1 and x1 so that it can then do our regression and figure out how to tell us what the actual equation is. And we need to change this equals out for the tilde, the weird squiggle, which is right over here. So y tilde and y1 is equal to b, or tilde, bx to the power of 1. Oh, and I forgot my a. How did I do that? A, b to the x. There we go. So y1 tilde a b to the x1. We just take our equation of an exponential function. Y is equal to ab to the x. We change these to the ones, so they reference our table, and we use the tilde, and it finds exactly the line of best fit for us. And it'll look at our a value, which is 1,000, which we already had found. The b value is 0.5, or a half, which is what we'd already found. And we have our r squared value for how confident are we that exponential is a good fit for this relation. And it's 1. And if you remember, the closer to 1 this r squared value is, the better the fit. So this is 1. This is a perfect fit. This is definitely a exponential relationship with those parameters. So that's something you can do to test as well. So we didn't do this part, so don't worry about that. But this is a good fit. And yeah, I think that's everything you need to answer all the questions on the practice.